Hi folks, my name is Scott Wilkinson, and today I'm going to be breaking down my most recent publication, The Limitations and Potential of Non-Parametric Morphology Statistics for Post-Merger Identification. And while that title might sound quite wordy, I'm going to try and describe it to you today in terms that should be understandable by the general public. Let's see how well I can do that, and let's get into it. First, the most important piece of context for this work is to consider that galaxy mergers play a pivotal role in the evolution of galaxies over time. And yes, while galaxies, when we look out into the night sky, do appear to be relatively static and unchanging, they do evolve, and quite dramatically, throughout their lifetimes. And it's for this reason that studying galaxies and identifying them in the universe is of a very, very high importance for those that study galaxies and galaxy evolution. Because in order to really understand what's driving changes of galaxies in the universe, we have to understand galaxy mergers and their role in all of this. For even more context, here's a simulation of a galaxy merger as if it were being observed from one of the world's largest telescopes on Mauna Kea. You can see in the video on the left that these galaxies start off as nice, orderly spiral galaxies, and as they start to interact with each other gravitationally, their spiral arms unfurl, and then upon the actual merger event, their shape becomes completely destroyed, leaving behind this kind of less orderly, chaotic, elliptical galaxy. And this is known as a transition from spiral morphology to elliptical morphology. I'll loop the video for you one more time, but this time I ask that you pay attention to the plot on the right, which shows the star formation rate of the system as a function of time in gigayears. You'll note that at the beginning of the simulation, the stars are forming a very typical number of stars, say 5 to 10 stars per year. As the galaxies merge together, this increases by over a factor of 100, and then rapidly decreases to almost no stars being formed at all. And this exemplifies that it's not just the morphology of the galaxies that is changing, but key properties of what's going on inside the galaxy as well. One critical problem with studying galaxy mergers is that over the course of an entire lifetime of a galaxy, the window over which it's observable as a merger is actually quite small. And this means that when you actually go out looking for galaxy mergers, they happen to be quite rare and quite difficult to find. So one key problem that my paper looks to solve is to understand how well we can actually detect galaxy mergers when we look for them in the universe. In order to answer that question, I'm going to take a sample of 424 simulated galaxies that have recently undergone a merger and come from the simulation looking something like this. I'm then going to take each of those galaxy mergers, view them from 4 different viewing angles to give me kind of different orientations and more statistics, and degrade their images to different qualities. In essence, I'm adding noise and adding blurring to make them more realistic. And the result looks something like this. For every galaxy merger in my sample, I have a grid of 36 different images of different image qualities. From left to right in this grid, the images become noisier and noisier. And from top to bottom, the images become blurrier and blurrier. The result is, in the top left corner is the worst quality imaging you could imagine using. And in the bottom right corner is the best quality imaging we might have over the next decade. Now, in each of these different 36 image qualities, I have thousands of images of galaxy mergers. If we imagine going searching for galaxy mergers, how effectively can we find galaxies at each of these image qualities? Another way to think of this is if your friend is on the other side of a big room, how loud does that room have to be? How noisy does that room have to be before you can no longer hear them and understand that they're there? Moreover, how many pairs of glasses that aren't your prescription do you have to put on before you can no longer see that that's your friend? And on top of that, which one's more important? Is it the ability to see them through the glasses, or is it the ability to hear them? This is exactly the question I'm trying to answer in regards to looking for galaxy mergers. Now it's time to get into the nitty-gritty details of how I'm going to assess whether a galaxy is detected as a merger or otherwise. And if you remember from my title, I'm going to be using something called non-parametric morphology statistics to assess if a galaxy is a merger. Now, non-parametric morphology statistics are really just this big a wordy way of saying that we're going to take the entire galaxy image and reduce it down to a single number. And hopefully that number will be more meaningful and will help us parse whether this galaxy is a merger or otherwise. There are many examples of this, and I use several of them in this paper, and they've been used historically to identify galaxy mergers for 10, 20, almost 30 years now. To keep this video short, I'm going to discuss the result of only one non-parametric morphology statistic today. That is one of my favorites, asymmetry. Now, the asymmetry statistic is fairly self-explanatory. It's really just a measure of how asymmetric the galaxy is. And if you think back to that video that we had previously, galaxies are quite symmetric before and after a merger event. But while the galaxy is undergoing a merger, all this kind of chaotic gravitational influence causes a galaxy's shape to become asymmetric. The more asymmetric it is, the more likely it is to be a recent merger. Considering the grid of 36 different image qualities that I showed you earlier, this is what the results look like for the asymmetry statistic. If you look at the results for the completeness grid in blue, you'll see that in the worst quality imaging, the imaging that is in the top left corner, precisely none of the mergers in my sample are detected at that image quality. As you go from left to right, which if you remember from the image I showed earlier, is less and less noise, more and more mergers are detected. Then, as you go from top to bottom, more and more mergers are detected as the blurriness improves. And from the top left to the bottom right, the combination of low noise and low blurriness goes from detecting no mergers to 42% of the mergers in my sample, which is not great, but definitely an improvement over 0%. If you look at the false positive rate grid in red, you'll see that as image quality improves, as you get closer and closer to the bottom right corner, there's an unfortunate side effect of improving the image quality so that you can detect more mergers. Namely, that as you improve the image quality, non-mergers, so just regular, secularly evolving galaxies, are being detected as galaxy mergers. That is to say that as the image quality improves, the slightest deformation in a regular galaxy is now being caught by this high quality imaging and inferring that this is a merger. So that means that there's actually a trade-off between detecting more galaxy mergers and incorrectly identifying more normal galaxies as galaxy mergers. And this leads to a decreasing in purity as you go to higher quality imaging. So that is to say that in the highest quality imaging tested here, only 64% of the mergers that you detect as mergers are really mergers. And so that's not much better than guessing randomly in this sample. So this is actually not working as well as you might expect. The results for the asymmetry statistic are echoed across the other non-parametric morphology statistics tested in this paper. And thus, the paper is titled The Limitations of Non-Parametric Morphology Statistics for Post-Merger Identification. That being said, there is one much more promising result that is important to include in discussing this paper. That is, that if we take all of the individual non-parametric morphology statistics and combine them together with a very simple machine learning algorithm known as a random forest, we can actually dramatically improve upon any of the individual statistics. I won't bore you with the plots about the random forest, but suffice to say that when using the random forest machine learning technique, we can achieve a completeness of 89% and a purity of 84%, meaning that there's no trade-off between identifying more mergers at the cost of incorrectly identifying non-mergers as mergers. The paper goes on to discuss other factors that affect galaxy merger identification, including things like the mass ratio between the two galaxies. So if a big galaxy is merging with a much smaller galaxy, that's much harder to detect than two big galaxies kind of colliding head on, as well as things like gas fraction and total mass of the system. One last thing that I'd like to talk about in this video is something that I couldn't actually include in the paper because I really need a video format to show it, and I think that it's really cool. This is to say that in the paper, I do a 2D kind of figure about how the different viewing angles affects the non-parametric morphology statistics and your ability to detect mergers. I'd like to show you kind of a video representation of the different viewing angles of any individual galaxy. It looks something like this. All right, so what I'm showing here is on the left-hand side is another galaxy merger image from the simulation that I've generated at varying viewing angles. And those viewing angles are being tracked on the right-hand side by the gray square moving in this kind of map. And the map is not so different from just like a global projection of the Earth that you might have seen before, except instead of projecting it into a kind of rectangle, I'm projecting it into a oval. And so as the viewing angle changes, the color of the map on the right-hand side changes according to how well the random forest machine learning algorithm is able to detect this galaxy as a merger. So at first, when it's being viewed face on, you can see all the different kind of asymmetric and strange galaxy features that clearly make this thing a recent galaxy merger. And the random forest produces a probability that's near 100% prediction that it's a merger, and so it's in the orange. But then later on, when it's viewed edge on, in kind of two different orientations, you have these kind of purple blobs in viewing angle space in the map on the right-hand side, where the random forest, our best ability to detect this galaxy as a merger, can no longer detect this galaxy as a merger. There's just no way around it. The merger features simply aren't there to be detected. There's just some fundamental upper limit to our ability to identify galaxy mergers in the universe. And that is that we're only viewing them from one viewing angle, Earth. And if it doesn't happen to line up with a viewing angle that's showing us its merger features, if they're hidden behind the galaxy or in some other orientation, then we're never going to be able to detect this galaxy as a merger, no matter how fancy we are. So if you've made it to the end of the video, I want to thank you for spending your time here with me and learning about galaxy mergers, non-parametric morphology statistics, and how well we can identify galaxy mergers in the universe. I recognize it's a bit of a niche issue, but I think it's kind of assessing a tool that allows us to study something critically important to the assembly and evolution of galaxies and the universe itself, and as well as kind of project forward as to what we might expect the future of the Milky Way to be. And I think that's really cool. So if you have any questions or if I've missed anything or you want to talk about it further, leave me a comment, send me an email, and I'd be happy to talk about it. So again, thanks very much and hope to see you in the next one.